All right, welcome back. We are continuing our discussion of momentum. We've discussed what is momentum. Well, it's emotional quantity that multiplies mass and velocity. We discovered that a interaction can be defined by an impulse, that is force times time. And then we've discovered this idea that for a cleverly defined system, that momentum is conserved, meaning that if you calculate the momentum of the system before something happens, that value that you find is the same exact value that will be found afterwards, just like it was with conservation of energy. But this does raise the question, what do we mean by a cleverly defined system? And there's a very good definition for that. When we take a look at this video, our goal is to learn how to define or to determine whether a system is closed, because it is a closed system that conserves momentum. Now, there are really two sort of requirements for a system to be a closed system, for it to conserve momentum. So there's two requirements, two rules that a system must follow. The first is that mass must not change. Whatever your system is, the total mass that is in your system cannot increase, cannot decrease. It must stay the same. In this case, we would like to use if we'd like to use this sort of calculus definition, right? Let's introduce a little bit of calculus. We're to take the derivative of mass with respect to time. This is the rate of change of mass. The rate of change of mass, well, that should equal 0. So we should get no rate of change of mass. In other words, if we look at a graph of mass versus time, whatever mass we begin with is the same amount of mass that we will always have. It'd be a straight flat line. So this is the first requirement, that mass must not change. And you might think, okay, well, this is an obvious requirement. I hesitate to say that because there are systems where mass does change. The second thing that must be true. The second thing that must be true is that there must be no net, I'm writing that big and bold and underlining it for a reason, there must be no net external forces. And why this is important to be specific about the net, it's because net forces that are external to the system are going to exist. There's almost no system where there are 0 external forces. So there's always going to be individual external forces. But the point is that when you take those external forces and you add them together, that they should cancel each other out. And we've seen this a few times. We would write this mathematically as the net external forces, and sometimes we just write this as F external, understanding that this is meant to be all of the external forces together. The net external force should equal 0. And if our system meets these requirements, we say that it is a closed system. And if it is a closed system, then it conserves momentum. So this is the idea. It must meet these two qualifications. So let's look at a system and sort of game it out. Figure out, can we determine the net effects on an object? See, does it change mass? And we'll start off with the same system we had in the previous video, where we had two cars, and I'm going to draw my janky looking cars here, heading towards each other. To first determine the system, it's often helpful to start with one of those interaction diagrams. And the interaction diagram would have car 1 and car 2 obviously in it. So let's draw out our interaction diagram. Car 1, car 2 on the right hand side. I'm going to actually redo car 1. So we have car 1 and car 2. Obviously, these two cars are going to interact with each other. I'm going to call that force FC for F of the collision. So over here on the left-hand side, all right, FC equals the force involved in the collision. If we were to take a look at car 1, that would be the force of 2 acting on 1, F2, 1, just like in the last video. Or if we were to look at car 2, it would be F1, 2. But for right now, I'll just say that the interaction that is between them is the collision. Okay, well, what else do we have? We have a surface, and the surface interacts with both of these cars through a normal force. And then we have the gravitational force, so we have the entire Earth that is present. And for the entire Earth, they interact with both cars through the weight. We'll ignore friction, and I'll explain why friction is a nice negligible force a bit later on. But for right now, these are going to be our forces that are present. We take a look at car 1. If we were to look at the system of, let's say, for example, car 1, I'll outline it in green here. If we were to look at the system of car 1 would have the external forces, and I'm drawing only the external forces. The external forces are the ones that cross the boundary between environment and system. So if we were to look at car 1, we would have the normal force upwards, the weight downwards, and we would have the force of car 2 pushing on car 1. And we look at this system and we say, well, normal force equals to weight. So those two would cancel each other out. And in this case, the external force on the car is going to be F21, which is definitely not equal to 0. So we would look at car 1 and we would say car 1, if we define this green bubble, just car 1 as our system, it would be a not closed system. So it would be not a closed system because we have some external forces. Well, what about if we look at car 2? Car 2 would follow the similar sort of problem, that we would have normal weight and force of 2, that would be force of 1 on 2. And we look at this, the normal force again cancels out the weight, and we have F external equaling F12, which again does not equal 0. So in this case, when we define our systems as being each car separately, if we define our system as being just the left car, we do not have a closed system, meaning momentum is not conserved. If we look at car 2 would have the external force of car 1 pushing on car 2, meaning it is not a closed system, meaning the momentum of car 2 changes. But if we make a clever decision, to consider the system to be both cars in total, and you can always define a system to be multiple objects. I could include the surface here in our interaction as well if I wanted to, but I'm going to leave it at just these two, these car 1 and car 2. If I were to take a look at car 1 and car 2 as being the system, we have the environment being everything outside the blue bubble, that is the surface in the entire Earth, and we have now our system as being everything in our bubble. And we take a look at the interactions that are crossing that boundary between environment and system. We have the normal force, the weight, the normal force and the weight of car 1 and car 2, but this interior interaction of the collision, well, that doesn't cross the boundary. That interior collision force is within, it's held within our system. It is an internal force, not an external force. So when we draw our free body diagram here, and again, our free body diagram only considers the forces that are external to our system, meaning that we will only have the normal force on car 1 and the normal force on car 2 going upwards. We would have the weight of car 1 going downwards and the weight of car 2 going downwards. Those are our 4 different interactions that cross our boundary. And we know that the normal force is equal to weight for both of the cars. So what does that mean? That means that if we were to take this and map out what the external force is, the net external force, well, it's going to be the normal force minus the weight, those all cancel each other out, meaning that the external force here is 0. Meaning that when we consider both cars together, When we consider both cards together, we get this external force equaling 0, meaning momentum is conserved. Well, that's at least rule 2, right? Rule 1, does the mass change and our two cards are going to collide? The matter isn't going anywhere, it's still maintained in our system, so we can be sure that the mass is conserved here as well. So this meets both of those rules, both of those requirements, that the mass does not change and the external force is not 0, or the external force is 0. So we have a closed system here, and this closed system will conserve momentum. All right, so what are some cases of maybe a little bit more complex ideas, right? Well, perhaps we were to look at something like, I don't know, a rocket. We'll look at rockets in a little bit more detail in a later video. Oh, my iPad just freaked out. So here's my picture of a rocket flying through space. And you ask, why does a rocket work? Well, a rocket works because of the law of conservation of momentum. But you might be tempted to say, okay, I'm going to define my system to be the rocket. But what's interesting here is a rocket's mass changes. A rocket's mass changes because as it is flying through space, it is ejecting fuel. And as it ejects fuel, that ejection of fuel is actually what propels it forward. But as it ejects fuel, the change in mass over time does not equal 0 if we just determine our system to be the rocket. So you say, okay, well, then this is not a closed system if you just consider the rocket itself. The rocket itself, it doesn't have any external forces acting on it, right? It doesn't have anything in space to be acting on it. We're going to assume it's far enough from the Earth that there's no gravitational force, or it's far enough from anything. There's no gravitational force, there's no friction force out in space. So there's no external force on our rocket, but the mass changes over time. So by just taking our definition to be the rocket, well, then we don't have a constant mass, meaning that our rocket is not a closed system. So instead what we'd want to do is include the fuel into our rocket. And if we include the fuel into our rocket, well, now we have no external net forces. Again, there's nothing out in space for it to interact with. And including the fuel inside of our system then makes the change in mass equal to 0. So our rocket does not change in mass in the second definition, the blue circle, where we include the fuel inside of it. All right, so these are sort of the two looks at what defines a closed system. We're going to be spending most of our time looking at this idea of collisions, and we'll spend some time looking at this idea of rockets. And the reason why I like looking at rockets is because, rockets are fun in space and all of that, but it's actually the same physical principles of why, like, a squid and a lot of sea creatures, they propel themselves through the same ideas of rocket physics. Okay. So in the next video, we're going to discuss types of collisions. There are several types of collisions. And with these collisions, we are going to discuss sort of how we can implement conservation of momentum with them. All right, so I think that's good for now. If you have any questions, feel free to reach out. Otherwise, I'll see you in the next video.